Okay, so I suppose I'll get started. So I welcome the viewers to this problem solving and live interaction session for the subject for the course experimental stress analysis, uh, being offered by Professor K. Ramesh on the SWAYAM portal. My name is Ganesh Ramaswamy. I'm a PhD scholar in the Department of Applied Mechanics and Biomedical Engineering. I'm working under the guidance of Professor K. Ramesh and Professor U. Saravanan. So today we will be discussing the contents of week 11, which has essentially to do with temperature compensation and other aspects to strain gauge analysis. So let us go ahead and look at the first question. So the question says self-temperature compensation gauges can be used in general for which of the following? It can be used for a particular material, can be used for any material, it can be used only for steel or only for aluminium. So I'll just give a brief about what the self-temperature compensation gauge is. So essentially, temperature also contributes to change in resistance and thereby change in strain in the context of a strain gauge. So what happens that if you have a specimen and if we have a strain gauge pasted over it, for example, let this be the strain gauge pasted over the specimen. So what happens? Let us say this has a coefficient of thermal expansion of alpha S, and let the strain gauge have a coefficient of thermal expansion as alpha G. So the change in resistance. So the change in resistance brought about by this difference in alpha or the coefficient of thermal expansion contributes to a change in resistance given by alpha S minus alpha G subject to a known temperature change. Also, because there is change in temperature, there will also be a change in the resistance of this metal foil itself by virtue of that temperature change, not because of this uh, differential expansion, but there would be a contribution SC delta T, where this accounts for change in resistance due to delta T in the foil, or rather I should say change in resistance in the foil, in metal foil, due to delta T. And this component here, this accounts for change in resistance, or rather this accounts for the strain brought about by differential expansion or contraction. So in this context, what is a self-temperature compensating gauge? It has been found after much research that this alpha G and ST can be modified for a particular alloy. It can be modified by bringing in certain impurities and certain processes such that the resultant of this sums up to zero. So whatever change that is brought about in the resistance and whatever alpha G it has, if this can be tweaked such that for a given alpha t, these two cancel out each other. Then the temperature change bears no effect on that strain gauge. So such strain gauges are known as self-temperature compensating gauges. So STC, this is also known as STC gauge, such that let me call this equation some number. Let me call this equation 1. Let's call this equation such that equation 1 equals 0. And naturally, this has certain limitations. This can only be made for one particular material. For if we go for a different specimen material, then this adjustment has to be tweaked in order for this to be nullified. So this is very specific to a particular material. This is specific to a particular material because this has to be chosen in such a way that these things nullify out. Good evening, Mr. Sivakumar. Could you just confirm if you're able to hear me all right? Okay, very good. Thank you. Thank you very much. Yeah. So this self-temperature compensation gauges can be made such that we tweak these two values so as to nullify this change in resistance brought about by the temperature. And this is applicable for certain alloys where we have control over it for a given range of temperature. If the range of temperature goes too high, then naturally we also saw in the last session that the alloy behavior itself changes due to temperature. So this also has that limitation, but nonetheless it is possible. So this is the concept of self-temperature compensating gauges, which is used for which changes from material to material. Okay, so let us look at this question. The loss in signal due to the lead wire resistance is best represented by which of the following, where RSG is the resistance of the strain gauge. So let us see first what this actually implies. Say that I have a strain gauge like that. And this has been connected using lead wires to a Wheatstone bridge where this comes from the supply. And we have another tap here, which is the second resistor. And this has been, and we try to measure the output out of this given a change in mechanical strain, which brings about a change in the resistance. So this is the input, this is the output that we try to measure. This is the Wheatstone bridge. Now what happens is this strain gauge has a resistance of RSG. Now we see that these are two lead wires that are connected. So let us say that these lead wires are also metal. So this will have RL as the uh, as the lead wire resistance. So in this case, if we see the total resistance of this arm includes the lead wires also, and in certain applications, for example, aircraft industry and so on, the lead wires can be meters long, multiple meter, hundreds of meters long. In such a case, any change brought about by temperature to these resistance of these lead wires also adds to disturbing the not only the sensitivity but also the balance of the Wheatstone bridge. In such a case, if this is too long, the initial balance itself can be affected, which cannot be corrected by the amplifier. And we may have to take note of the actual reading, whatever it is showing, and then we may never be able to bring it back to zero. So we will have to take that as the benchmark and proceed with it. And this brings in a lot of complications. For example, if I were to have this long wire and if I go and touch it with my hand, if the uh, if the thing is such that if I touch it with my hand, we imparted some heat and that changes the resistance. If you are making many minute measurements, that also will contribute to a strain which is actually not brought about by the mechanics of the problem that we are trying to study. So in such cases, there is loss in the signal. Why? Because we saw that R1, R2 by R1 equal to M, which needs to be 1 for maximizing the output of the maximizing the signal output. Hence, this gets disturbed. This totally disturbs this balance, and that loss in the signal brought about is given by the ratio of the net lead wire resistance divided by the resistance of the strain gauge. So this is the measure what we make in loss of signal due to the lead wire resistance. Now, as professor also shows in the lecture, I'm sorry, 1 minute. As professor also shows in the lecture for one particular length, we see how much resistance the lead wire has and how much it contributes to the uh, how much it contributes to disturbing the initial balance of the strain gauge. So this needs to be accounted for. There are ways and means to do it by if we are using a quarter bit circuit, we can make certain modifications to this in order to nullify this effect, which we will see subsequently. That is known as a three-wire temperature compensating arrangement that we generally do for a quarter wave. I'm not sorry, not quarter wave, quarter bridge arrangement. Okay, so let us look at this. Basically, there are multiple manufacturers of strain gauges, out of which Vishay Micro Measurements or the Micro Measurement Group based in US is one main body, one main company that provides this, and they have a designation system. Now, why this is important is naturally, if one researches, one can find this. But in the interest that people are familiar with everything, at least with everything, the basic rudiments that has to do with concept to commissioning of a stress analysis using strain gauges. Professor has also included these terminology so that we are not totally lost when we take a look at that. So in that interest, every strain gauge has a particular code. They don't go by. So when we ask for a code, uh, we may have to mention this code, or we may have a catalog from where we need to select this. So each of these terms relates to something. So the first two relates to the carrier matrix, that the backing that is used, then the foil, then the self temperature compensation number. Then we have the gauge length, which is given in mils, because they don't use the metric system, they use the imperial system, and other aspects to it. So this also changes from company to company. There are a couple of more companies that are shown in the lecture. So it just serves as a ready reckoner for anyone who wants to brief themselves with how the strain gauge designation system works. Granted, this may also evolve over time, and Vishay might come up with a new set of nomenclature. But nonetheless, it is important that one is aware that something like this exists. Okay, with that background, if we see this question, in the following designation by the micro measurement groups, which is the Vishay micro measurement group, what is the what is represented by 250? So we are able to see EA06 250 BG 120. So what is asked is what does this 250 represent? So here we can see the 250 represents the active gauge length in mils. So this represents the gauge length in mils, which is nothing but 1,000th of a, which is 1,000th of an inch. So what does this imply? This is 250 mils. So this is 250 by 1,000 of an inch, which is 1/4 inch. Now, if I were to convert that to mm, just to get a basic idea of how much that would be, just 1/4 into 25.4. So this will be around 6, or 25.4 by 6. This is around 6.35 mm. So this represents the gauge length. Okay. Similarly, in this, what is represented by the 120 at the end? So the 120 at the end, as we saw here, it represents the resistance of the strain gauge in ohms. So this represents the strain gauge in ohms. Granted, some of these things might be very straightforward, but just for the sake of completeness, it has been included in the lecture as well as the assignment. So I've also taken that up. Okay, so let us look at this question. At a point in a biaxial stressed material, for example, we have, let me take the example of a cruciform specimen. So I hope you, if you don't know what cruciform specimen is, I'll just explain it. We'll have smoother ends. There won't be sharp ends actually. So here in the plane of the sheet, what we can do is we can subject this to different biaxial stresses based on our need in order to either study a problem or characterize a material and so on. Oh, excuse me, just 1 minute. Yeah. So if this is sigma 1, or rather I should say sigma, uh, let us say sigma x or sigma y. So there will be some biaxiality ratio, which is sigma x by sigma y or vice versa. And this we can adjust. This will have a particular range where we can adjust and try to study how the uh, how the thing comes about. But this is a case where we actually know where that it is in a biaxial stress field. Now, in such a case, this is for a problem that is known. Let us say that we have a similar case where we know that the state of stress is biaxial, some shear, some shear exists. Now we know that the state of the stress is biaxial and the principal stress directions are known. So for this problem, we know that this is the principal stress direction. If we know one, we know the other because both are mutually perpendicular. If this direction 1 and direction 2, then which of the following choices will be optimal to calculate the strain? And by saying that calculate the strain, we mean how will we populate the strain tensor. So the strain tensor for this planar case will have four components. Basically, this will be epsilon, let us say xx, epsilon xy, and epsilon yy. So in general, we need at least three components to populate this strain tensor. But once we know the principal stress directions, if we are able to actually install strain gauge in these directions, we can actually find the components of strain along 1 and 2. So this can again be transformed by simple transformation. I can get this as epsilon 1, epsilon 2, and I know in the 1, 2 coordinate system, shear strains do not exist. So in order to populate this stress tensor, I need only two measurements. I need to make the strain measurements only along those two directions, which is why this is often clubbed with brittle coatings, where we will see that there is a, for example, there is a crack that has formed here. We know by this very crack pattern that one of the principal stresses has to be perpendicular to it. So from this crack measurement, we actually know at this point what is the direction of the maximum principal stress, and thereby we also know the direction of the minimum principal stress. So if we orient our strain gauges in such a way that we are able to make measurements along 1 and 2, we can easily populate the strain tensor. This might look like a minor aspect when we are dealing with a single strain gauge, but for a problem that has thousands of strain gauges installed, even reduction of one channel per strain gauge means a lot, and it will contribute to a lot of uh, saving in the long run. I think this got duplicated. Okay, I suppose this is clear. Yeah, in such a case, which of the following choices would be optimum to calculate the strain tensor at the point? Will it be a rectangular rosette, a delta rosette, a T rosette, a stacked delta rosette? Now we know that a stacked delta rosette measures strain at that very point by placing three strain gauges one over the other, but this might not be suitable from bending application because that in that case, for bending, the strain varies linearly like that. Strain varies linearly. So if the first strain gauge is here and the second is stacked one over that, so there is a difference in the level, which will basically lead to strain being measured at different planes away from the neutral axis, which means it is not correlating to a single mechanical problem. So stacked delta rosette has that issue. Nonetheless, delta rosette and stacked delta rosette have three strain gauges. A rectangular rosette has strain gauges like that, 0, 90, and 45. A delta rosette might be like that. So a T rosette basically has two strain gauges, which measures one like that, and the other one measures strain like that in two perpendicular directions. So a T rosette would be an ideal choice for measuring the or populating the strain tensor at a point where the principal stress directions are known for the case of a biaxially stressed material. So I suppose this is clear. So let us move to the next question. Okay, so here we see this question says there is a strain gauge of 120 ohm resistance. So we have the resistance of the strain gauge as 120 ohms. Is pasted on a stainless steel specimen at a distance of 100 meters from the instrument. So we have the specimen here. We have the strain gauge pasted like that, from which the tabs go. and this is connected to, so we have the input like that. So this is the input and the output is measured from here. Now due to some constraint, this is said to be 100 meters long, this distance. Now what this does is this will introduce a change in the resistance because of the resistance of the lead wires. That is what we are trying to see here. So for this case, the lead wire resistance, this will have RL. This already is told that this is 120 ohms. Very well. So it is said that it is at a distance of 100. So the length of the lead wires is 100 meters connected to a 0.5 mm copper lead wire. So the diameter of the lead wire is 0.5 mm, which is given. Now we are talking about the measurement taken at room temperature. At room temperature, calculate the effective gauge arm resistance connected to the Wheatstone bridge of the instrument in a 3-wire circuit to that of a 2-wire lead circuit. Given that the specific resistance of copper, so mu of copper, rho of copper is given to be 1.5 E minus 8 ohm meter. So let me just be brief about what this. So from here, as we saw, we take this. This is the input, and we have another resistance like that. So this is the output. This is the arrangement that we have for a quarter bridge 2-wire circuit. So this is the 2-wire quarter bridge arrangement in which this is RG, which this has a resistance of RG. This is RL, total RL, for 2 wires. Now in a 3-wire arrangement, what we do, we just make this modification. So we will just take this, cut it out and connect it here. So that is all that we do in a 3-wire arrangement. So what happens is the resistance of this wire goes into the input instead. And what we have now is one arm of the resistance is Rg plus RL. And since we have Rg equal to 1, 2, 3, and 4, so for the fourth arm also this becomes Rg plus RL. In which case we know that adjacent arms cancel out any change in the uh, Wheatstone bridge, in which case this Rg plus RL would be cancelled out by this Rg plus RL, and whatever change in the resistance brought about by this alone due to the mechanics of the problem will be easily measured. So this is the this is a three wire quarter bridge arrangement. Granted, this RL and RL are maintained the same. Okay, so in this case, so what is the total resistance of the arm here? Just a moment. So the resistance of the arm, effective resistance of the arm is Rg plus 2 RL. And here the effective resistance of the arm remains Rg. Why? Because this RL and this RL is cancelled out and we are looking at the resistors alone. So what the question asks is, what is calculate the effective arm resistance connected to the Wheatstone bridge of the instrument in three lead wire circuit to that of a two wire circuit. So what is Rg upon Rg plus 2 RL is what is asked. Now we know that Rg for this case is 120 ohms, and we have been given the specifics of the lead wires. So let us go ahead and calculate what is the lead wire resistance. So the resistance, yes sir, yeah, no, this has already been cancelled out. Whatever is brought about by this is cancelled out, right? Yeah, yeah, okay, okay. So here the resistance of the lead wire is given by rho L by A, where rho is 1.5 10 power minus 8 into length was 100 meters divided by area. We know that it is zero point 0.5 mm is what is given. So pi d power 4 by pi d square by 4. I'm sorry, not d power 4, d square by 4. So this comes out to be 0.5 square pi by 4 into 1.5 into 10 power minus 8 into 100. So this comes out to be 7.639 ohms. So this is the resistance of one lead wire which is 100 meters long made of copper with the specific resistance of 1.5 into 10 power minus 8 ohms. So therefore the ratio comes out to be 120 by 120 plus 2 into 7.639, which is 120 by 7.639 into 2 plus 120, which is 135.28, which comes out to be 0.89. Very well. So the ratio, the effective gauge arm resistance connected to the Wheatstone bridge for this case of 3 wire to 2 wire comes out to be 0.89. Very well. Okay, so let us look at this question. Which one of the following statement or statements are true for a self temperature compensating gauge? So what is asked? And initially we saw what self temperature compensating gauge is. Essentially, I'll just provide a brief recap. It says, so the change in resistance brought about by the temperature is given by Sg into alpha S minus alpha G into delta T. This is the differential strain between the specimen and the gauge, where the gauge is made of a metal foil that is a different material as compared to the specimen that we are trying to check. And also, there is a change in resistance brought about in the alloy because of the change in temperature, which is accounted for by this Sp. So in self-temperature compensating gauges, we will tweak these values by appropriate impurities and control in the material manufacturing, such that this equation goes to zero for a given range of temperature. So in such cases, we can use that strain gauge without worrying about the temperature effects for a given for a given range of temperature. Because if the temperature range goes too high, too big, then naturally the property of the alloy also will start changing, because as we saw, we have one behavior like this, and then the isoelastic alloy, it has a very steep gradient within a very small range of temperature, which makes it unsuitable to actually make self temperature compensating gauges with that alloy, and so on. The STC accounts can accommodate I square R loss, yes, whatever is inherent due to the resistance, due to the heating, it can account for that. STG, this is, yeah, STC gauges can accommodate for small changes in the environmental temperature. Yes. Can it account for the large temperature? If one is true, the other won't be. But naturally, why this is because the alloy behavior also is very much dependent on the temperature range, on the working temperature range that we are actually adopting. CC ranges work like superconductors. They don't work like superconductors. They have a non-zero resistance. So they don't work like superconductors. If they were superconductor, there won't be any resistance. In which case, we are only trying to study the change in resistance brought about by the mechanics of the problem. So that would defeat the entire purpose. So that is not the case. So SPG gauges can account for this loss due to heating, as well as it can accommodate small changes in the environment. Okay, so I take it that is clear. So let us look at this question. What are the benefits of a three-wire circuit in a strain gauge? As we saw just now, what three-wire brings about is it increases the measurement sensitivity How? Because when we have a two-wire circuit, we have Rg plus 2RL as one of the arms, which is not equal to the resistance in the second, third, and fourth. That is the dummy resistor that we are taking. If we take a 120 ohm gauge and we connect it to the instrument by selecting 120 ohms, it will have the connected resistors as 120 ohms. But eventually what we are connecting is 120 ohm plus 2RL, in which case M, which is R2 M, which we saw as R2 by R1, is no longer equal to 1, which actually reduces the sensitivity. So this is for a two-wire case. For a three-wire case, this is circumvented, which is why it provides increased measurement sensitivity. It is used for strain measurement in static loading. Yes, essentially for dynamic loading, because of introduction of slip rings, etc., we might not be able to always afford to go for a three-wire circuit. In which case, we'll try to minimize it, as it is said in the lecture also. If there is a slip ring, then its connection to the nearest point we can afford by having a smaller wire or a two-wire circuit. But for static applications, this would be the most ideal choice for having the effect of lead wires cancelled out. So this is very much useful for strain calculation in static loading. It does provide automatic temperature compensation. We need not account for the temperature compensation, because what is brought about in one arm gets cancelled out by what is brought about in the adjacent arm, thereby nullifying its effect. And this is an intrinsic bridge balance, meaning we don't have to, by the very arrangement of the bridge, we have been able to accommodate for nullifying this effect. We need not bring about any additional correction factor. So it is intrinsic to the bridge balance. So yes, this is very much true. So the benefits of a three-wire circuit are essentially all of these. Okay, so let us look at this question. Which one of the following statements are true for maximizing the signal for strain gauge measurement in a Wheatstone bridge is what is asked. So if we have a strain gauge and this is measuring a particular strain component which is along this direction, along the gauge length. So if we have a full circuit of the same strain component gauge, meaning let us say that we have the classic example of a cantilever subjected to some stimulus at the end, some delta or P, and we are trying to measure the strain gauge at this location. This we have as strain gauge 1. And let us say from the top view that we have all the strain gauges pasted like that. We have the 4 strain gauges, let us say they are pasted like this, adjacent and symmetrical somehow. So we know that this is trying to measure strain along this line and nullifying any end effects. Essentially, the strain measurement would be same in all of these 4 gauges. So call this 1, 2, 3, and 4. Now, if we were to go for a full bridge arrangement and we connect it. So we know that strain gauge 1 is Sg epsilon, sorry, so the change in resistance in 1, delta R1 is Sg epsilon 1, delta R2 is Sg epsilon 2, but epsilon 1, 2, 3, 4 all are measuring the same strain component, is what is said. Now, if we were to connect this to the strain gauge as a full bridge circuit, we would essentially have the similar strains cancelling out because we have 1 minus 2 plus 3 minus 4. So essentially, this will lead to a zero output. So we won't be having any change shown in the reading. So this is, but if we were to place 2 and 4 somewhere else, maybe the bottom, as we see in one of the problems, then this would naturally give an amplification of 4 because of light strains. But for the same strain component, a full bridge arrangement is not the way to maximize the signal output. It is in fact the way to nullify it, which is not serving our purpose. So if we increase the bridge voltage, yes, we would essentially see a we would essentially see a boost in the signal output by increasing the voltage. By increasing if we are increasing, decreasing doesn't apply. Increasing the resistance of the strain gauge, yes, this is also true, as we saw that the change in resistance is brought about by Sg epsilon A, which is essentially, so greater the R, greater will be the change in resistance, and greater will be the sensitivity. So increase in the strain gauge resistance is another way to maximize the signal for the strain gauge measurement. Okay, so I hope that is clear. So let us look at this question. Which one of the following strain gauge or strain gauges should be used for getting residual stress measurement by drilling of a hole? This is naturally a sort of refer back and answer kind of question, but I'll instead give a brief on what this drilling hole method is all about. So let us say in general, for example, if we take the example of an I section, when it is actually made, will have residual stresses, will have some residual stresses. For example, the material is not stress free. Now, how do we make measurement? Let us consider this place, this portion, and I consider it to be over here. Yes, but the strain is essentially bringing about a change in the resistance. That resistance will definitely change. Change in the resistance will definitely have a subsume effect because of the resistance that you have taken. Strain remains the same. See, when we take the instrument and we actually input Sg, so no matter what the strain is, this even if the strain is same, for a different gauge, strain gauge, our resistance measurement will be different, which is accounted for. So what would happen is, even though strain has nothing to do with the resistance, strain is from the mechanics of the problem, what we are trying to measure, but the effect that it brings about in the change in the resistance, which makes our output amplified. That resistance, what we have selected for the strain gauge, definitely has a bearing on that. That is what you are saying. I understand. Epsilon is from the mechanics of the problem. What I take as a strain gauge resistance, why should it make a difference to epsilon A? Epsilon A doesn't change. But epsilon A, we are trying to measure it indirectly. We are not trying to measure the actual strain there. We are trying to correlate it through a Wheatstone bridge by what epsilon A brings about into delta R. So that is why selection of the strain gauge base resistance plays a role here instead of the actual strain. Actual strain is still the same. Even if I were to check this by some other means, let us say photoelastic coating, there also actual strain is still the same. It doesn't, that makes no bearing on what method we are trying to adopt. Yeah, it is just in the context of the strain gauge how we maximize the output signal. Okay, okay, yeah. So here, which one of the following strain gauges should be used for getting residual stress by drilling a hole? Yeah, so drilling hole method, what it does, this already is under some strain. Let us say that this is the state of strain at that point. It is having some generic state of strain brought about because of the manufacturing process or whatever. So what we do is generally we will drill a hole here. So once we drill a hole, whatever strain or stress that is logged in, that is the residual stress, it gets relieved. So if I were to paste a photoelastic coating here before the drilling and then do the drilling here. So as soon as I do the drilling, there the stress, residual stress in the measure in the specimen gets relieved. It gets relieved, and what does it do? It starts getting delivered to the surrounding area, and that surrounding area is over which we have pasted that coating. So the coating gets stressed. Once the coating gets stressed, it will start showing fringe patterns. So if we have a way that we paste a coating over there and then we drill a hole, we take an image before and after drilling the hole. So we will be able to correlate that with what kind of residual stress was built up at that point. So this is the basic idea behind the hole drilling method. Now, if we apply a photoelastic coating, we will be able to see the distribution along around that point. Rather, what we do if we were to take that point, paste a strain gauge here, keep monitoring the measurement. We drill the hole. We will see that there is a spike in the strain over there, which can be correlated to what was the residual stress or strain that was built up at that point. So that is another way to do it. So here, if you see in the lecture, the RE, R is the designation given to the strain gauges, which can actually measure residual strain. Basically, what will happen, it will come not as a single strain gauge, but as a strain rosette. So if we have the hole here, they will have recommendations that you paste it like that. So we will have a strain rosette, delta or T, whatever. So that we will paste it at a point, and then essentially it will look something like that. So if this is the point where we are trying to find the residual stress, here we will have one gauge length in this direction. The another gauge length will be in this direction. The third will be like that. So once we paste this, initially all the strain gauges are unstrained, so to speak. As soon as we drill the hole, we will have the measurement of the components of strain along three directions, from where we can essentially find out the entire strain tensor due to the residual stress at this central point. So this is how in the lecture the diagram for this strain gauge is actually shown, so that you can just take a look how it looks. So these are the ones that essentially have are designed to measure the residual stress or strain at a point by the hole drilling method. So I take it this is clear. I'll move on to the next question here. Okay, so the question says a strain gauge is pasted on an aluminum specimen kept at room temperature. So we have an aluminum specimen and a strain gauge is pasted onto this, and this is at room temperature at T equal to 25 degrees. Given that resistance of the strain gauge is 120 ohms, sensitivity of the strain gauge to temperature St is 8 into 10 power minus 5. Coefficient of linear expansion of aluminium. So this value alpha S for the specimen. S denotes the specimen here. S is 23.5 into 10 power minus 6 strain microstrain per degree centigrade. Okay. And then we have coefficient of linear expansion for the gauge material is given as 0.3 into 10 power minus 8. Sorry, minus 6 microstrain per degree centigrade. The strain sensitivity of the strain gauge Sg is given as 1.5. Answer the following questions. Oh, there seems to be only one question. Okay. Answer the question for the data given. If the room temperature is elevated, if the room temperature is elevated to 50 from 25, that is delta T happens to be plus 25 degrees centigrade. Calculate the change in resistance of the strain gauge pasted on the aluminum alloy. So as we saw here, for the strain gauge, temperature can bring about a change in resistance due to one is differential expansion or contraction with respect to the with respect to the specimen material, unless the strain gauge is also made of the same material as the specimen. Since the alpha is different, there would be some differential expansion or contraction which will bring about the change specimen material, and also the temperature effect on the resistance itself of the metal foil. So that change in the resistance of the strain gauge due to temperature, due to this delta T, is Sg into alpha S minus alpha T delta T, plus this accounts for the first effect here. The second effect is accounted by the sensitivity, temperature sensitivity of the strain gauge to the actual change in the temperature. So here Sg is given as 1.5 into alpha S is 23.5, alpha G is zero point 0.3. So this is 23.5 minus 0.3 into 25 plus 25, which is the change in the temperature, plus St is 8 into 10 power minus 5 into 25. So what does this come out to be? 1.5 into 23.5 minus 0.3 to 10 power minus 6 into 25 plus 8 into 10 power minus 5 into 25. So this comes out to be 2 point. Just a moment. Excuse me for 1 minute. यार कोई साल ही है I'm sorry, I just need to be excused for 1 minute. I'll just be back. I'm sorry about that. Yeah. So this comes out to be 2.87 into 10 power minus 3. So from here, it follows the delta R. So this gives me delta R is equal to R is 120 ohms for this. So this is 120 into 2.87 into 10 power minus 3. So the change in resistance. போட்டு இப்படி திருப்பி திருப்பி எடு is 120, which is 0.34 ohms. Okay, I hope that is clear. So let us look at this question. Handling the temperature effects has two components, minimizing heat generation and improving heat dissipation. One can improve heat dissipation by choosing the appropriate gauge pattern instrumentation schemes, which can also be used to minimize the temperature effects. So one is that we are using as a temperature compensation gauge, that is STG we are using, which accounts for the difference in the strain bit of the strain gauge versus the specimen material, and also accounts for the change in the resistance of this metal foil. But this is not the end of the story, because this strain gauge we have to connect to a Wheatstone bridge and then make the measurement. So that is where the lead wire resistance also comes in, which can also bring about an error in the measurement due to the resistance of the lead wires interfering with our problem, with our strain measurement. So in such a case, some of the installation schemes are given to connect the strain gauge to the Wheatstone bridge. As we discussed here in one of the problems, where we saw here, we had four strain gauges connected like that. We have a cantilever, but the strain gauges are connected in a particular manner where sorry, where 1 and 3 are connected on the top, 2 and 4 are connected on the bottom, and we have both connected at the same distance, which means in this measurement, epsilon 1, the strain in gauge 1 is equal to strain in gauge 3 will be equal to the negative. I'm saying because we have the downward load, so this will be under tension, this will be under compression, but of equal magnitude. So this will be minus epsilon 2 equal to minus epsilon 4. Okay, so here, which one of the following bridge arrangement or arrangements ensures implicit temperature compensation? So here we have a bridge that is 1, and then we have the 3 dummy resistors here. Now we know that strain in 1 doesn't account for whatever the strain that is brought about in 1 is okay, just a moment. All right, so this question does not specify that these are self-temperature compensating gauges. So there would be some change, although all the strain gauges are same. In which case, whatever effect that is brought about in 1, we can take advantage of the fact that delta R1 by R1 minus delta R2 by R2 plus delta R3 R4 by R4. This plays a role in our output. Hence, if we are not using self-temperature compensating gauges, we may as well connect it in such a way. If we have 2 or 4 resistors at our disposal, we may as well connect it in such a way that the effect brought about in one gets nullified by the other. So in this case, we know that epsilon 1 is equal to minus epsilon 2. So this arrangement has only epsilon 1. So naturally, the error that is brought about by epsilon 1 is not getting nullified by anything else. So this is not an ideal choice. If we go for the second arrangement, 1 and 2 are connected opposite to each other, in which case this 2 actually comes in this position where these two will actually get added. So this will lead to more error, in fact. Whereas here it is connected in the adjacent arms. So whatever the error that is delta R due to temperature that is brought about gets cancelled by delta R due to temperature because of 2. So 3 is definitely an arrangement that we can go for, and so is 4, because we see that this will give the same output but have a greater amplification, in which case 1 and 2 nullify each other, 3 and 4 nullify the errors in brought about by each other. So 3 and 4 are ideal arrangements for affecting temperature compensation. Very well. Now the question says, if a self-temperature compensation gauge is used, which one of the following should be chosen to ensure temperature compensation? Now here we have qualified that these four gauges are STG gauges. So whatever the error that is brought about in one due to temperature automatically gets addressed by its very design, because it is designed to in such a way to nullify expression, this expression. Okay. If that be the case, then which is an ideal arrangement to ensure temperature compensation? Again, we know here, now this is a comparative scale that we are looking at. In this arrangement, we have two quarter bridge arrangements, which are one in the same, because this is connected to one arm and this is connected to the other arm. It implies the same thing. Whereas we have two other cases where we actually have connected the voltage here, and we have tapped it and connected it to 4. One is connected to the strain gauge. So essentially, this is a three wire temperature compensating circuit. Similarly, if we look here, this is also a three-wire temperature compensating circuit. So given a choice in this problem, this strain gauge, the effect of the temperature to the strain gauge itself is addressed by the very fact that it is a STC strain gauge. And further, to nullify the effect of the lead wire resistance, we have two options that actually offer a three-wire temperature compensating circuit. So those will be the ideal choices for us to make the measurements and address all issues related to temperature. That is, compensate the temperature effects without the need for any additional corrections at a later stage. So this is how we address temperature issues. So as we can see that clearly, although strain gauge is very effective, temperature has a very major role to play in such problems. So at site also, when we are making the measurement, for example, if there are cases where they are making strain measurement on rails, in order to uh, in order to nullify the effect of the inherent temperature there, they would also have a test piece of rail placed on the side, which is not connected to anything, and they would be making measurements of strain on that very piece also in order to nullify the effect of the temperature due to nullify the effect of the ambient temperature on the strains. So the sum and substance of the session is that we have to be sensitive to the fact that temperature plays a very major role in our strain measurements. And if this is not accounted for properly, then this could lead to erroneous results. So which needs to be kept in mind. So I hope that is clear, and I hope I've done some justice to explaining how this comes about. When I've run out of questions, if there are any questions you have, I'd be happy to take them now. Uh, yes, sir. Yeah. Okay. Yeah. ST. Okay. I see. Okay. Okay. I might have to look at that question. Why don't you post it in the forum and we'll try to address it there? Yeah. No, alpha G is the temperature. Alpha G is the coefficient of expansion. Yeah, you can just take a look. Essentially, the strain gauge has a constant, which when we multiply by the temperature, it accounts for the change in resistivity of the strain gauge due to the temperature. ST. ST, whatever be the symbol, so that is one component of it. Then there is, yeah, ST. Then we have two other, because this actually what this does is because if we see any conductor, if we take, if we reduce the temperature to a minimum, then naturally resistance also reduces. This is how superconductors behave, for example, I'm saying. So the resistance has the temperature has a bearing on the resistance of that this thing. So that is what is accounted for by this constant, which when we multiply with the temperature, it accounts for that change. Secondly, there would be a change brought about by the differential expansion or contraction, where alpha G and alpha S are coefficients of thermal expansion of the specimen and the gauge respectively. Yeah. Okay. 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 All right. All right. Okay. Yeah. Okay. No, we have one expression now, R1 R2 by R1 plus R2. No, N plus delta R3 by R3. Let us say that this is the case. Now, is there any change brought about in R1, R2, R3, R4? In case of a quarter bits, these don't apply. So we have only this, and then there will be some factor of the voltage and things like that. So with that, if you calculate, you're not getting the answer you're saying. Yeah, yeah, okay. So delta R is given. This into V, yeah. So this is given. These three go to zero. This is given. Other things are given. Yeah. Ah, okay. Okay. Well, you just try it out again. If yeah, yeah. So in case of a quarter bit, essentially there will be no change in resistance 2, 3, and 4 because these are dummy resistors. Well, this ratio would also come. You just account for this also. This doesn't have any change essentially. So you can just account for this also and see if it matches. If it doesn't match, then perhaps you can post it in the forum and we'll take a look at that. Okay.